Hello and welcome. In this video, we're going to talk about voltage sources. So voltage, we learned, is our potential to have a current flow through our circuit, and that potential generates a power consumption over here. And without both of those two, without the current flow, meaning one pathway for current to get all the way down to the negative terminal, and the potential between the positive and the negative terminal, we don't have any kind of movement or power in our circuit. So potential is seen right here. With no potential, we see that the orientation of our valence electrons are all over the place. They were oriented when they were discharged, and then they stayed in that orientation. The second that we give a negative and positive flow to it, we see that those negative electrons point at their positive terminal, right? That's our valence electrons with our force behind them. And so now we have a potential to flow, right? It is not flowing though, because there is no actual negative back to its other lead. So we can characterize voltage in terms of work and charge. We can say that our voltage is equal to the work that we have divided by the charge that we have, right? And remember, that's just our potential to have the flow, right? So that means that there is no time involved in our voltage. Our voltage can be present at any given time at the same exact magnitude. And until we actually have current flow, time is not a factor for us. So let's go down one here and we'll look at what our voltage sources incorporate. So we have ideal voltage sources. That's what we're going to work with in Multisim. Here's a DC ideal voltage source and an AC ideal voltage source and a current source even that's ideal. And those ideal ones, we can always assume that they are true for our analysis. They're going to give a constant voltage and current at any voltage and current value that we want. And we can represent both AC and DC voltages and currents with them. Practically though, our Multisim is doing us a lot of favors for this. We'll see that the voltage decreases slightly as current increases in a practical source. So if we are actually using a battery and we start adding more and more and more components to it, we'll see that that voltage that we expect to be, say, 5 volts is going to slowly dwindle down, and it's going to be less and less total potential over time. And also, the current will always be drawn from a battery supply or a source voltage if there is a resistance. And so just like our wall outlets, if there's nothing plugged into the wall outlet, then there is no pathway and there is no resistance attached. But the second that we apply something to our wall outlet, we end up providing a resistance, a pathway to current, and that flow begins to flow. Right? And so that means that we have to unplug that device before current will stop flowing. Right? So our potential can be caused by batteries. Our battery terminals will give both a positive and a negative. This is an example of a salt battery. We see that this is our positive terminal on this side and our negative terminal on this side. And we can see that because of the ammeter flow. It says that the negatives are flowing towards the positive, which also tells us about this cathode. This cathode is copper. Right? And that means that those electrons really like that copper terminal and they want to flow towards it. So that's an opportunity for those to get into that other positive state. They're going to match and level out and eventually neutralize this flow here. Right? And we do have this salt bridge here. This salt bridge allows us to flow electrons back and forth. And that gives us that entire cycle rotation there. Without that salt bridge, this battery doesn't work. Same goes for this zinc cathode here. And we see this zinc cathode looks like it's been eaten up a little bit by its negative solution over here. Right? Remember, this is going to represent our negative solution, which means that it's going to be the part that is going to consume something. So as we transfer the energy into this anode here, it's going to consume the anode slightly until eventually it breaks it down. Right? And that's where our barrier stop on this. Either we break our salt bridge or we end up wearing out the zinc anode and having to replace it. And we see that in water heaters too, right? Where our anode in there stops us from eating up the case of our water heater, right? Because our water heater is aluminum, so that zinc is going to dissipate faster than the aluminum. And that's the intent for that. We want it to be the thing that electrons want to flow through. And so we give it as a sacrifice. Right, but we can build batteries out of any other thing that's going to provide us with a potential, a positive and a negative, just like these two solutions did. Right? We look at these two solutions. One of those is going to be liking positive charge, being able to hold the positive charge, and the other one's going to be liking negative charge, being able to hold the negative charge. Right? And they're both made out of salt. They're both salt potentials. So we're going to go down one here. This is going to talk about our fuel sources. So we can have fuel sources that consume energy over time. The battery is going to eventually drain and we're going to have to give it more supply. But this is going to consume a fuel source and use that to produce a potential. And so in this case, we're going to look at the hydrogen fuel cell. That gives us an electrochemical energy. This one's real cool. This one produces a DC voltage out of hydrogen. And hydrogen is one of the most abundant substances that we have. Right? It's in salt water. We can make salt water into hydrogen, and then we can use this device here to quite literally rip the electron from the hydrogen molecule. We'll send that electron that we ripped from the hydrogen around through a resistive load, like a motor or a heater or a battery. We can use it to charge. And then after that, we will allow that electron to flow back into the other side or cathode of our device here. And that is where we allow the hydrogen, the oxygen that we provide at the top, and that energy, that electrode, to go back together and produce hydrogen, H2O. So this device consumes hydrogen and produces H2O water, right? And it never actually uses all of that. The only thing it really consumes from that would be the potential for us to get hydrogen back out. So it creates pure water. And so that's called the polymer exchange membrane, if you want to look that up for more information about that. It's a PEM filter. The other one we have here is a solar cell. We saw that a little bit earlier where we were able to harness the energy from the sun. And we do that by the sun providing the negative part, our electron flow, and we capture it using this anti-reflective coating here, and that's our negative potential side. Right? And then we have an N and a P region, our negative and our positive region, and then the depletion region in between there. And that depletion region allows those negative ions to travel across right there. And then we'll have a conductive layer on the bottom. We'll use that as our positive potential. So we're quite literally comparing the net negative that we captured on top with the positive potential on the bottom. And that is going to allow us to have a current flow, right? It's going to give us a DC output. Okay, let us know if you have any questions.